So if that's the area of, that's the way I've drawn it, a circle, what's the formula for the area of a circle?
2 pi r.
It's the other one.
Oh, wait.
Oh, you now combine them.
Uh,
That's volume of a rectangular solid.
Is it 2 pi d?
No, 2 pi r is the circumference.
Is that what I just said?
You said 2 pi r squared eventually.
I did. That's not it.
I was working under the assumption that everyone knows two formulas. They have difficulty remembering which is which, but that's why I said it's the other one. Pi r squared, just pi r squared. 2 pi r is the circumference, pi r squared is the area. So, pardon?
We were in the ballpark.
Yeah, yeah. So r is just my area there, the 0.000111111 divided by pi, and then take the square root. And this answer is going to change your life. I feel like I'm neglecting you, dude. Just I keep looking at that direction. I know you're there.
I'm a new man.
Oh, yes.
0059470084.
All right, so where's the decimal point show up?
At the beginning.
Is it 0.00?
Yeah. I thought I said that.
I got 0 point.
Oh.
0.00594829. But anyway, close enough.
So Andre, you're getting it there, and
Yeah.
Hunter, you're getting it there.
This
Yeah, I got
0
2 zeros. What?
You got 0.00?
0.00.
Ah, okay, okay. Sorry.
Whatever. That's what I do.
All right, so 2 zeros after the decimal point. All right, then you're insane. Okay. So that's the radius. The original question was diameter, so just double it for the diameter. Anyway, we're talking about 10-meter long, and the diameter is a little over a centimeter. Something like that. Now, one of the reasons I bring it up, it's more than just spewing letters and numbers all over the board. When I asked how long it was going to be, we started out with 10 meters and expanded a little bit. But in reality, it actually expands in every direction. It's not like nature looks at it and goes, ooh, that's the long side, so that's the way it's going to go. It expands every way. If the diameter is small compared to the length, it's generally ignored. And so, fortunately, I picked numbers so that this length right here was roughly 1,000th of the length that way. That's considered very small.
I was gonna say, is that small? What you say?
Physics typically has a 10% rule. Much smaller than is if it's 10% or less of whatever the bigger number is.
This is probably a math thing, but I'm still stuck on why when you flip the fraction or 3 kg over v and multiply each size.
Okay.
That's how I got the 9. I thought that's what we were supposed to do.
All right, so why you didn't divide by 3, is that what you said?
Why we didn't flip the like multiply by the, like flip it? You know what I mean?
Okay, if we flip both sides, then we have v over 3, and over there 1 over 2,700. And then you can multiply both sides by 3. And you get to the same place.
Is that it?
1 over 8,100.
Oh, but all right. So when you're isolating the unknown, so in this case v, we need to start peeling away the layers. We got, right now, it's being shackled by this division of 3. We have to undo it, and you undo it by multiplying. So if we multiply this side by 3, we get rid of that division by 3. And if we multiply that side by 3, we gotta multiply that side by 3. So ultimately, you're multiplying 3 times 1 divided by 2700.
So, but the 3 doesn't times the 2700? I think that's what I'm doing wrong. Because I keep getting 8100 for 3 times 2700.
Yeah, the difference is, I can turn anything to a fraction by sticking it over 1. That's the math problem we're dealing with, so you multiply the bottom, multiply the denominators, you multiply the tops.
That's what I did wrong.
Okay.
Got it.
You said multiply the denominators and then multiply?
So when you're multiplying fractions, you multiply the numerators, the top part, and then you multiply the denominator, so 2700 times 1, which is 2700.
I think you're smart, Mr. That's what we do.
Yeah, and then you can skip the 1 over 900 and just do the, okay, I got it.
3 over 2700 is also
Yep.
equally valid. Let's keep going. Yes. I assume some other people would ask questions if they have them. But let me do the dramatic pause. Okay. So I take a cube, and let's make it, we'll stick with grams, 10 grams. No, that's awfully small, we'll make 100 grams. 100 grams of aluminum cube. Think I'm hearing hiccups, or did he just leave? You have hiccups? No, I've got orange juice in the next room. Orange juice always worked for me.
Alright. If you can grab me some, that'd be great.
But the trick is, you have to drink it all in one shot.
Okay, that's fine, yeah.
That's what they told
So-
me when I drank too much liquor, mister.
Be quiet.
Since you're gonna have to take your mask off.
That's fine.
All right, so I got a 100 gram aluminum cube, and I stick it in boiling water. Over here, I have water in a container. And this water is at 20 degrees Celsius, or 293.15 Kelvin, just for the fun of it. And want to go with 150 milliliters. I'm going to take that cube after it's been sitting in the water for a while, and I'm going to transfer it immediately over into the cool water. And immediately the cube will start to cool down and the water will heat up. Question is, at what temperature will they stop? Now, I am going to make of course, some nice ideal assumptions here, or requirements. 1, no loss to environment, no energy loss to environment. I guess energy loss to, environment being anything that's not this water and that cube. Environment, try spelling this time. Non-cool water, non-aluminum cube. Trying to formalize it, probably just making it worse. Anyway, energy lost from here is going into this water and nowhere else. In the lab, I believe you did this specific heat lab. Yep. You're supposed to transfer it really quickly to minimize the amount that's lost into the air. Now, there's some information I did not give you, but we can figure it out. We do need to know the density of aluminum. Now, I've just written it up there in SI units, but I'm dealing with grams over here, so, and specific heat for aluminum and for water, I go in calories per gram degree Celsius, so let's stick with the less international standard and more tradition. So density of aluminum is 2.7 grams per cubic centimeter. That's it. Now, I'm not expecting you to have that memorized. It's nice if you do, but if you need that information, I would give it to you, usually at the top of the first page. I have 100 grams of aluminum. We need to figure out how big this, actually, what do we need to know? We need to know the mass of the cube. We have that. Actually, do I need to know anything else? Oh, I was going in to try to figure out what the size of the cube is, but we actually don't need to know that. So this information here is just for the fun of it, apparently. We do need to know the mass of the water. That part I am sure of. So, what is the mass of the water?
Is it 150 grams?
Yes, it is. The density of water is 1 gram per cubic centimeter. And how many cubic centimeters in the milliliter? That is correct. Cubic centimeter is a milliliter. So I have 150 milliliters of water, which means I have 150 grams.
What was the question you asked before?
Ultimately, it's what's the final temperature going to be?
Yeah, no, we said, what is?
I asked what's the mass of the water? I have 150 milliliters of water. What is the mass?
Mm-hmm.
And because the density of water is 1 gram per cubic centimeter, and a cubic centimeter is the same as a milliliter, which means that for every milliliter I got 1 gram of water. So 150 milliliters.
Yeah, 150 grams.
Yep.
Oh, okay. Yes, y'all just too smart. All I got for y'all.
All right, so specific heat of aluminum was written up earlier, but I'm going to, I think it's 215, yeah. 0.215 calories per gram degrees Celsius. Specific heat of water. This is liquid. Now, typically in everyday life, you say water, it's understood to be liquid. In science, it's not necessarily the case, but it is in this case. That's 1 calorie per gram degrees Celsius.
Are we looking for something?
Yeah, the final temperature. I'm going to take this cube from the boiling water, stick it into this water, and this is going to eventually, the cube's going to cool down, the water's going to heat up, and we're going to figure out what that temperature is, where they reach balance.
Oh,
Thermal equilibrium.
We did this the other day.
Yeah, okay. So, you understand it?
Sort
Okay.
of.
Or you go with you don't understand it at all and then just board out brilliant answers.
No, we don't wanna do that.
Oh.
Flying joke.
All right. So the concept, cube is losing energy, heat, water is gaining energy. So whatever the cube loses, the water gains. Math-wise, the heat from the aluminum plus the heat from the water equals 0. One of the Q's will be positive, one will be a negative, because they're related to the change in temperature. Let's flash back to that formula. Q is equal to MC delta T. Change in temperature for the cube is going to be a negative number because it's cooling down. So I can just, depends on where you want to stick the math, but I'm just going to take Q over Q water to the other side. So whatever energy lost by Q from the aluminum is equal to the negative Q for water. Stick a formula in there. So this is mass of the aluminum times specific heat of the aluminum times the temperature of the aluminum is equal to the negative mass of the water. I'm just going to use H, so I don't have to write as much. Times specific heat of the water, times the change in temperature of the water. Plug some numbers in. Now, I'm starting out with temperature in degrees Celsius. I'm going to end up in degrees Celsius. So I'm not going to write units because I know where I'm going to end up. So this was 100 grams of aluminum times 0.215 calories per gram degree Celsius times the change in temperature, which is the final temperature, which is what we're trying to find, minus the initial temperature. What is the initial temperature of the cube?
Well, are we doing it in Celsius?
Yes.
Wasn't it 100? It's boiling water.
I hope so. If it's in the boiling water long enough, it should be the same temperature as that. So minus 100 equals negative of mass of the water, which we figured out was 150. Specific heat of the water, 1, times the temperature change in temperature of the water. So that's the temperature minus the initial. Starts out at 20 degrees Celsius. There's a whole lot of lines there. Let's see if we can make it look a little bit nicer. I'm just going to multiply those together. And I can multiply those together.
Can I ask?
Yes, ma'am.
The cube isn't inside of the 20 degrees Celsius water.
It starts out in the boiling water to get it up to 100 degrees Celsius. And then we're going to transfer it over. We're going to take that cube and stick it in here.
Oh, that's what we're doing.
Yeah. So that's 21.5 times T minus 100 equals negative 150 times T minus 20. If nothing else, it looks less cluttered to me. Now what do we do with that? What's the math operation?
Does it become 21.5 T and then you multiply 21.5 with 100 to get the left side?
It's called distributing. So we're going to multiply this times that, and that times that, this times that, and that times that. And if I got something in parentheses like that with a binomial, because I got two things inside here, two nomials. If I got a binomial with a number outside, I can distribute. I multiply this times the first thing and this times the second thing. So I get 21.5 minus, well, 21.5 times 100 is 2150 equals, negative 150t plus 3,000. And I lost my t over here. 21.5 t.
And then that's,
Said FOIL? FOIL is a more complicated version of this. Yeah, it's half of a FOIL. More of a FOIL. All right, so now I've got it down to here. I need to get all the t's on one side, things without t's on the other. So I'm just going to add 150 to both sides, because the math people still tell me that I can, as long as I do it to both sides, I'm good. And this way I get rid of my 150t over here. And then I got that 2150, I want to get to the right side, and so I just add that to both sides, because I'm subtracting here, so I want to do the opposite. And that gets rid of that over on my left side. So where I end up so on my left side, I got 150t plus 21.5t, so that's 171.5t. And on the right side, I got 5150. And that's as far as I can do the math in my head. Next step will require a calculator.
30.029.
Say it again.
30.029.
For t. And units?
Celsius?
I'm going to nitpick.
The 3 Celsius?
Yeah, there we go. Don't do this nitpicking.
I do.
All right. Does this answer make